In this video, we're going to start with the Maclaurin series for sine of x. And we're going to differentiate it and show that it equals the Maclaurin series for cosine of x. Again, what this is really highlighting is the relationships we know between functions, their derivatives, their antiderivatives. Those relationships are preserved even when they're expressed in their Taylor series or power series form. So let's go ahead and start with the power series or Maclaurin series representation of sine of x. It's equal to the series from n equals 0 to infinity, minus 1 to the n, times x to the 2n plus 1 over 2n plus 1 factorial. And what we're going to do is take the derivative of both sides with respect to x. So on this left-hand side, we know from calculus A that the derivative of sine, that's equal to the positive cosine of x. And what we're hoping to show is that when we differentiate that right-hand side power series or Maclaurin series for sine, is that we get the Maclaurin series for cosine popping out. So let's see what happens. Well, we have our derivative. We want to take a derivative with respect to x of whatever's on that right-hand side. However, the only thing that has x's attached to it is that x to the 2n plus 1 power. So we can really think about that this series or this derivative passes by the summation n equals 0 to infinity. It passes by the minus 1 to the n because it has no x is attached to it. And it doesn't touch that factorial, the 1 over 2n plus 1 factorial, because there's no x's attached to it. So we really have the derivative then only wants to act on that x to the 2n plus 1 term. And again, we're hoping to show that what's coming out of this right-hand side after we take the derivative is equal to the Maclaurin series for cosine. So that's why these question marks are there. So let's just continue looking at this right-hand side. So this series n equals 0 to infinity, the minus 1 to the n. We have a 1 over 2n plus 1 factorial. None of that changes. But the only thing for us to focus on is what happens to that x to the 2n plus 1 when we take a derivative with respect to x. Well, we have a variable raised to powers, and we're taking the derivative. So this is going to be a power rule differentiation. The power being the 2n plus 1. So if we differentiate x to the 2n plus 1, that power will come down in front. So we'll have x or 2n plus 1 quantity times x, but now raised to that power, the 2n plus 1 minus 1. So we'll just have x raised to the 2n power, because when we differentiate variables raised to powers, we deduct 1 off of that power. All right. Now let's see what we have on this right-hand side now. We have this minus 1 to the n. We have a factor of 2n plus 1, which we can just write upstairs in that fraction. And down below, we have a 2n plus 1 factorial. And that's all times x to the 2n. And again, what we're hoping to show is that this series is actually equal to what we have for cosine. And well, if we look at what we have compared to the cosine series, we have this minus 1 to the n. That's in the cosine series. We have this x to the 2n, which is in the cosine series. But in cosine, we don't want a 2n plus 1 factorial. We want a 2n factorial. And well, you might be seeing where we're heading now. We have this 2n plus 1 in the numerator of that fraction. We're going to be able to cancel off a factor of 2n plus 1 from that denominator's factorial. So let's do a little bit of factorial algebra here. So we have that minus 1 to the n. That term is fine. We have the 2n plus 1 in that numerator all over the 2n plus 1 factorial. We'll come back to that in a moment. And we still have that x to the 2n at the end. And what we're going to do now is take that 2n plus 1 factorial and just use some factorial algebra. So we can rewrite this as a 2n plus 1. And then using factorial algebra, that's going to be times 2n factorial. So what we see happens is those 2n plus 1s will cancel each other from the numerator and denominator. So on the right-hand side, what we're left with is a series from n equals 0 to infinity, minus 1 to the n. We now have x to the 2n all over 2n factorial. And this series is the Maclaurin series for cosine. So what we've just done is basically show that when we take a power series, like for sine of x, and differentiate it, we still see the same relationships between the functions and their derivatives that we see between the power series representations and their derivatives as well. Those relationships are preserved. The derivative of sine is cosine, so the derivative of sine's Maclaurin series is equal to the cosine Maclaurin series.